Howdy. The point of this video is to discuss how to index crystallographic planes using the Miller indices. So why do I want to describe a plane? Well, there are lots of two-dimensional features, surfaces, interfaces, boundaries, in crystal structures that I would like to be able to describe and define. Here are a couple of quick examples. If I'm looking at martensites, so this is twinning in a martensitic structure, and the twinning is observed along very specific crystallographic planes in a structure. Another example would be if I'm looking at the grain boundary between two neighboring crystals. So that is the interface separating two individual crystals, each with their own unique orientation. Finally, if I want to describe crystal habits, so these are free planes in a single crystal as the crystal is growing. So if I want to describe these surfaces, I also need to describe them in terms of crystallographic planes. And we do this using the Miller notation. So let's try some examples. We're going to start off with a general triclinic axis, so three lattice vectors, different lengths and not perpendicular to each other. And say I have this particular plane that I want to describe. So there are basically three steps that we need to do to index a plane. We need to look at the intercepts. We need to take the inverse. And we need to reduce any fractions. Okay, what do these steps mean? Step number one, intercepts. Where does this plane intersect with the three principal lattice vectors? Or what are the fractional coordinates of those intercepts? So this is pretty obvious for one of them. For B, it intercepts at 1. But it's not so clear where it intersects the A and C axes. And this is generally the case. You know, for the plane that's illustrated in some unit cell, you might need to extend that plane to figure out where it intersects these axes. So we're going to do that. I see that this line here, if I kept extending it, would intersect the C-axis up at 2. Similarly, I need to draw an extended line here, or I could come from this side, passing through 1/2, and I see that it intersects the A-axis also out here at 2. Now this might be a little bit hard to visualize, so take a moment and try and work it out for yourself. So I know the intercepts. I would encourage you at this point to start with a table. The intercepts here are 2, 1, 2. The next step is to take the inverse of those. 1/2, 1, 1/2. So 1 over 2, 1 over 1, 1 over 2. Now, this is kind of tricky, and this is oftentimes what people forget. When we're doing directions, we don't take the inverse at all. When we're doing planes, we do take the inverse. So students oftentimes confuse the two. So just a word of caution. The third step is to reduce the fractions. So here we see fractions. I'm going to multiply this all through by 2, and I'm going to get 1, 2, 1. So I have to multiply all three of these numbers through by the same number in order to reduce the fractions. And if I were to write this in the standard Miller notation for planes, that is 1, 2, 1. I don't use commas, and I use round parentheses. So a single plane is described by round parentheses. So these are the Miller indices of this particular plane. Let's try a different case, and this is going to show us one tricky thing you might encounter. So again, my three steps. Find the intercepts, find the inverse, and reduce the fractions. So what are the intercepts? It's intersecting A over here at 1. It's intersecting B over here at 1/2. But it never intersects C. So this plane is parallel to the C axis. In this case, I would say that the intersect is at infinity. And to convince yourself why that is, think of two planes that are not parallel, but I'm rotating them so they're getting closer and closer to parallel. As I do that, that intersect point is going to get further and further away. And so when they are actually parallel to each other, they never intersect, or that intersect point is at infinity. So in my table, x, y, z, the intercepts are 1, 1/2, infinity. I'm going to take the inverse of these. That's the next step. 1 over 1/2 is 2. 1 over infinity equals 0. 1 divided by an infinitely large number is 0. I would then reduce, but I notice I'm already using integers only, so I'm all set. The indices of this plane are 1, 2, 0 using the Miller notation. So note, if I'm parallel to the C plane, my C index is 0. These are actually usually called HKL indices. So the L indice would be 0. Let's try another tricky one. Again, I'm always going to do these 3 same steps. I look for the intercepts. I take the inverse, and then I reduce my fractions. So where are the intercepts in this case? Well, to me, it looks like it intercepts A at 0, it intercepts B at 0, and it intercepts C at 0. So if I were to take the inverse of 0, 0, 0, I'm going to get infinity, 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 and this is not a really well-defined plane. So the problem is that I'm passing through the origin. So anytime the plane is passing through the origin, you need to do something to figure it out. You can either move the plane in the unit cell, or you can move the origin. The two are identical. Again, when you're indexing planes, just like directions, the absolute position does not matter. It's just the orientation of this with respect to the origin. So I am going to shift the origin so it's up here in the back left upper corner of this unit cell. So again, I'm going to take the intercepts. It intercepts A at 1, it intercepts B at 1, and it intercepts C at -1. So if I write my table at 1, 1, -1, the next step would be to take the inverses, but the inverse of 1 is 1, the inverse of 1 is 1, inverse of -1 is -1, so I don't need to do anything. I also don't need to reduce because these are all already integers. So the Miller indices for this particular plane are 1, 1, bar 1. So this is pronounced bar 1, and this is the notation, crystallographic notation for -1. Usually it's written like this. Sometimes when your professors are giving you homework assignments or making tests, it's tricky to get that bar in exactly the right place. So they will write something like this with the -1 sign. But the proper notation is 1, 1, bar 1. Okay, the next kind of a challenge would be if you were given the indices and asked to draw a plane. So here we're given HKL of 2, bar 1, so again that's -1 and 2. Now because this is a negative number, I know one of two things are going to happen. Either I'm going to be intercepting somewhere out of the unit cell, off in the negative direction. Well, that is going to happen. So the alternative would be to redefine to shift our axis off to the side. You don't have to do this. You can just extend your unit cell outwards. I find this to be easier sometimes. So we're going to do the exact opposite of the process from before. So I know the final notation. Essentially, I need to take the inverse of these. So the inverse of this is 1/2, -1, 1/2. And then these are now the intercepts. So the intercept with the a-axis is 1/2. The intercept with the b-axis is -1. And the intercept with the c-axis is 1/2. And so this plane is going to look like this. Again, you only need 3 points to define a plane, and because I shifted that origin at the beginning, it's a little bit easier because now it's all falling within that original unit cell. So with planes, remember that second step, taking the inverse, we need to do that when we're indexing planes, but that's not a step that's used when we're indexing directions.